This Multivariate Calculus webinar has two goals. First, I want to show some of the relevant Maple tools that are useful for Multivariate Calculus. And second, I want to show how resequencing of skills and concepts as applied to Multivariate Calculus can be implemented in Maple. Now, this phrase is taken from the literature, and it means that instead of stressing the development of manipulative skills that are then used to learn concepts, the process is reversed. Maple is used in place of those skills, and the initial emphasis is on development of conceptual understanding and insight. Then you can use Maple to implement the requisite skills, see how it all fits together, and the body of skills that the student needs to leave the course with, or that's postponed until after conceptual mastery has occurred. Typically, the Multivariate Calculus course starts with a unit on vectors, lines, and planes. So let's pick a problem, lines and planes, and see how Maple contributes to this conceptual understanding. Let's take this number 7. I want an equation for the plane that contains 2 points, P and Q, and is parallel to a given vector, which means that that direction has to be in the plane. So to begin, I'm going to install the Student Multivariate Calculus package, Tools, Load Package, Student Multivariate Calculus. There are many packages in Maple, over 100. It's all part of the Maple library. It's just a way of grouping the commands. And here I have typed the 2 points, P and Q. Use square brackets, that's lists, represents points. These angle brackets are inequality symbols, and that's how you represent a vector. So this is the vector V. If we go here to the context panel, Student Multivariate Calculus, Lines and Planes, and pick Plane, the pop-up asks for coordinates. The defaults are X, Y, and Z. I'm happy with that. This symbol represents a module, a container that has been constructed to hold all of the information about this plane, and then you can query this for bits and pieces of information. This is the information you can query, and right now I want representation, and so there's the equation of the plane. So the first thing is get an answer to the problem to see what it is that you need to accomplish. Now, the typical solution that one finds in a calculus book is a vector solution. So let's draw a picture to see what that vector solution is like. So this gray patch is a portion of the plane that we're looking for. These two blue vectors are position vectors to the points P and Q. This black vector is W, which you obtain by subtraction, Q minus P. So that has to necessarily lie in the plane. The red vector is the vector V, not quite collinear with the black vector. And the cross product, which would then give you the normal, is in green. And so process is obtain this vector W, take the cross product with V and W, get the normal N. You then have at least 2 points, so you only need one of them, point and a normal. That will give you the vector, the plane. The actual computation to bring this about would go like this. So I've pre-typed some of this stuff so that you don't have to watch me do a bunch of typing. P and Q, those 2 points, are represented as position vectors, so we use these inequality symbols to make angle brackets vectors. V is vector, direction vector, and R is the position vector to a generic point, and so all we need to do here is select assign name from the context panel, and Maple will assign those names to those objects. And we need this difference, W equals Q minus P, and if we do an assign name, I can't hold my hand steady. Assign name, Maple will do the computation and assign that vector to the name W. And then we need the normal, which is V cross W. So for this, I'm going to just drag this over. So I could write it or drag it over. The cross product symbol I got from my favorites palette. And it got into my favorites palette by finding it in common symbols. There it is. I right click on it because I'm in Windows and I have a 2-button mouse. You can do this on other 1-button mouse systems. Add to favorites. So I populated my favorites palette with a bunch of these things that I use regularly. And again, I'm going to do assign name. And then I'm going to drag over this equation, which is the vector equation of a plane. I'm going to just hit the enter key, and you can see the equation of the plane. And you might notice, now let me close this, that there's a factor of 2 that has been removed from the equation of the plane here, which is present here. Now, a couple of additional comments. When I type W equals, these vectors are in italic. I like the names of vectors to be bold Roman, so I just use these context or toolbar symbols to change the font, because it's just like how it looks. If you want to see what these vectors are, or we could type W comma N, hit the enter key. This is the vector W, and this is the vector N. Here's where that factor of 2 has crept in. So the plane command up here, that's operating up here, is a little bit smarter than just straightforward computation here. And then this problem is susceptible to an algebraic computation, which I'd like to show because it teaches something useful. I'm going to begin with an unknown normal. So here's a normal whose components are ABC. Now we'll do an assign name for that. Then I'm going to define a scalar valued function of a vector argument. So the argument is a vector. The components of the vector, because the name is V, are V1, V2, V3. And if you look carefully, this is N dot, and this could be XYZ. So N dot XYZ plus D, this is the generic form of the equation of a plane. So if I have f of v equals 0, I'm writing the equation of a plane, but I don't know what the parameters are. I need to find a, b, and c to determine this plane. So to define this function, I just used copy-paste, and I will use assign function. Now, this function has to satisfy some conditions. First of all, f of p has to be 0 and f of q has to be 0. And this normal has to be orthogonal to the vector v. So here are 3 conditions which will form 3 equations. But there are 3 equations in 4 unknowns. However, there are really only 3 unknowns. There's got to be at least one parameter that's not 0. You can divide through by that parameter, and then you really have only 3 things to calculate. So I'm going to solve these equations for A, B, and C in terms of D. So let's go here to solve. Solve for variables. I'm going to solve for A, B, and C. A, comma, B, comma, C. And then I would like to put this information back into this function. So this function, if evaluated at the vector r, which is xyz, is going to give me the equation of the plane. So let's do a substitute into here. Substitute into. And I'm going to substitute into f of r equals 0. And so you have the equation of the plane, but every term has a factor of d in it. And I think the simplest way to deal with that here is set d equal to negative 12. So let's do an evaluated point. Let's let d be negative 12. And I now have the same equation of the plane that I got earlier. So this is a useful device to define a function whose argument is a vector. After the units on vectors, lines, and planes, the course moves into some 3D stuff that's not linear. And so the notion of level curves and plane sections show up. And these are primitive tools for graphing a surface. But you have a tool like Maple, it will draw the surface. So what is the role of level curves and plane sections when you can actually draw the surface without having to get level curves and plane sections? So let's see if we can visualize level curves and plane sections. What kind of tools does Maple have for that? Okay, so here is an equation whose graph is going to be the graph of a surface. There is a tutor. Okay, tools, tutors. So there are at least 50 tutors. And it's spread out of these subject areas. So we have multivariate calculus, and there is a cross sections tutor. I'm going to launch it from the context panel. And to do that, I first install the student multivariate calculus package. So load package, student multivariate calculus. Then I need the expression whose graph is the graph of the surface. Student multivariate calculus, tutors, cross sections. So the cross section tutor launches. It has the function in it. The default is to have cutting planes z equals. There are 5 cutting planes, but the default range is 0 to 32. If you look here at the range in z, it's minus 150. So this range should be really changed to minus something like 140. And I'll go to 0. Actually, the top height's 4. If you look at the function, the top height is 4. Okay, so you do a display, and you get the 5 cutting planes, and you see how they form these level sets. I like to call them level curves when they're on a surface. These can be animated. Oh, let's make this more. Let's make it 25. And let's animate. Then you have one plane moving through the surface, and you can see the level curves being cut. And you can also do the same thing for plane sections. Just let this be x equals, and let's see, this is graph minus 4 to 4. Let's go minus 3 to 3. And so you have now a vertical plane slicing through the surface, creating plane section. If you hit close, the last graph you've drawn will be written to the worksheet, and you can see down here there is a command that's doing all of this graphing. You can copy and paste it and work from the command, but it's much easier, in my opinion, to work with this tutor where you just have to press the appropriate buttons and not have to worry about the syntax of the command. So let's do a close. And now you have this graph in the worksheet, and you can use the tools for animations. Now I've got it going back and forth to examine the behavior of that animation. I know I was asked many times about how to draw a surface and its tangent plane, so I'm going to do that problem next. It takes a little bit of progress into the course to get the tools you need, so this question wouldn't come up at exactly this point, but let's tackle it. So we have a surface. Here's the surface and a point on that surface, and we want to obtain and graph its tangent plane at that point. Okay, so in the multivariate calculus package, which I'm going to load, tools, load package, student multivariate calculus, we have some tools. And the tool that we want here to begin with is we want a normal vector, normal at that point. So if you have an explicitly given surface like we have here, a normal vector is, or it has components, minus partial with respect to x minus fx, I call it, minus fy1. On the other hand, if you had an implicit representation of the surface, then the gradient would be normal. So let's make an implicit representation. So this is what I've written. And now I want to take the gradient. Okay, so student multivariate calculus, differentiate gradient. Variables are x, y, and z, and the point 1, 1, and just think about it for a second here. If you put in a 1 here and a 1 here, you have a 3 and a 7, so you're subtracting 10 and negative 6. Just do that mentally. Okay, so now what happens is Maple has returned a list of gradient vectors, because you can give more than one point and you can have gradients at several points. So what we want to do here is select that object, so it takes it out of the list brackets. So that's the normal vector. So let's give it a name, assign to a name, and we'll give it the name n. Okay, so now we have a normal. So we make a sequence of the contact point 1, 1, and we know it's negative 6, and the normal n, And let's go to student multivariate calculus, lines and planes, plane. X, Y, Z are the variables. There is the plane representation. We want the equation of the plane, so we ask for its representation. And I'm going to isolate this and put in the form of z equals. So let's go to solve. isolate expression for z, and we have z equals. Now the graph. Well, let's do it in two stages. Well, first let's graph the surface. We'll go here to plots, 3D plot. Variables are in the order xy, and there is the graph of the surface. And all that's left is to take z equals, just take the stuff on the right hand side, and drop that onto the existing graph, and you now have a graph of the surface and tangent plane. Now, surprisingly, there's a tool in the vector calculus package which is even more powerful. So let's install the student vector calculus package. We need this expression for the function. And in the student vector calculus package, there is a command, tangent plane. And you can obtain a tangent plane at the point of your choice. Point of contact is 1, 1. And you get a vector representation of the parametric equations. X is x, y is y, z is, you can read it, 14 minus 6x minus 14y, which is what we had gotten here earlier. So this is a command that really should be in the student multivariate calculus package, but it's in the student vector calculus package. Now, it's also possible to work this from top-level functionalities, and in so doing, I'm going to show you a little trick that extends what Maple can do. For single variable calculus, the notation f prime of 2 means take the derivative and evaluate it at x equals 2. The closest you can come to that in multivariate calculus is the use of subscripts. F sub x at 2, 3 is take the partial derivative with respect to x and evaluate it at x equals 2 and y equals 3. However, you can't do that in Maple because Maple sees the function name f and the symbol f sub x as the same thing, and it doesn't distinguish. There's a trick to get around this, and that trick is make this symbol an atomic variable. So let's begin by defining f of x, y as the function f, because you're going to need that. So assigned function. Now, f sub x, that has to become an atomic variable. Now, depending on how you have your Maple set up, that may or may not turn out to be automatically an atomic variable. Mine is set up so that that would be a table entry and not atomic. For me to make that atomic, I have to press Control Shift A. So I believe you would find that in a one of these convert, well, maybe it's in format. Let's take a look. Yeah, it's in format. Convert to inert form, but it's already inert, so that's why it doesn't light up. And you see that the keyboard equivalent is Control Shift A. Okay, so that's atomic. And to verify that it's atomic, if you go here to View menu and you select Atomic Variables, then anything that's atomic shows up in this maroon color. So the symbol f sub x is atomic. It's a separate name, so it's now the name of a function. Which function? The function is partial derivative, So I'll go here to the calculus palette, take the partial derivative with respect to x, and apply that to f of xy. And make that a function, a sine function. Now I'm going to do the same thing with f sub y, but you got the explanation, so I'm just going to drag this over and do a sine function. So I'll leave that stuff red for a bit so you can see here. To get a normal vector, if you're writing with pencil and paper, you could write minus fx at 1, 1, minus fy at 1, 1, and 1. If you are unaware of this device that I'm now explaining, then this wouldn't work. But you can see here, these are atomic. I'm just going to drag this over. But before I can compute with that, you need to unassign the existing n. So we go to variables. You see that existing n? Right click and unassign, because Maple will not assign over something that's been assigned. So if I just now assign name, this vector will be computed, and I think I'm going to turn off the display of atomic stuff. Alright, so we need this vector, the position vector to the generic point, assign name, and we need the point of contact, which is f, which is 1, 1, f of 1, 1, so 1, 1 minus 6. So drag this over and assign name. And then we can use the equation of the plane in vector form. And if I isolate z, let's do solve, isolate expression for z, we get the same equation for the plane that we got earlier. So this was done to show this device about how to construct a way to use subscripts as partial derivative operators. Now, I always taught my students that the tangent line or the tangent plane was the first degree Taylor polynomial. So let's go about this calculation through the Taylor polynomial aspect. Well, there is a tutor, tutors, Multivariate Calculus, Taylor Approximation. That's the tutor I'm going to end up using here. So f of xy has already been defined. There's its rule. And if I go here to Context Panel, Student Multivariate Calculus, Tutors, Taylor Approximation Tutor, there's the function in there. I don't have to get the function into there. The point of contact is 1, 1, and I want a degree 1 polynomial, and I get a picture automatically of a piece of the surface and the tangent plane. And there is the first degree Taylor polynomial, so z equal to that is the equation of the tangent plane. You see here the command that's behind this, and if I hit close, I get the last graph drawn. So there's the picture that we were trying to get. Well, we've obtained the equation, and we've got that picture. Could you obtain that picture from first principles, just by construction? F of xy, hit the enter key, you get the rule. There is a series command from which you can get a multivariate Taylor polynomial. We want both x and y, and it's 1, 1, and degree 1. So there's the Taylor polynomial, do it interactively. Then to draw a graph, well, let's graph this plane. So we go plots, and there's the plane, and if we drag and drop equation for the surface, we have again constructed by drag and drop picture of the surface plus the tangent plane. And finally, from first principles, you would define partial derivatives as operators, which we've done, so we don't have to do that again. And then down here, recognizing that these subscripted f's are atomic. Here, let's verify that. See there in that maroon color. What you write for the equation of the tangent plane is exactly this. Function at 1, 1, derivative at 1, 1, x minus 1, derivative with respect to y at 1, 1, y minus 1. So if you just hit the enter key, this construction gives you the first degree Taylor polynomial. So after partial differentiation has been covered, then the applications come next. One of the first application is unconstrained optimization, or in a setting like this, it would be find the extreme points and classify the extreme points of this function. So let's give that one a try. So we have a function of x and y, and we want to determine any extreme points and what the classification of those extreme points might be. So let's begin by grabbing this rule, and let's give it a name. Let's give it the name f, assigned to a name f. Okay, now we want to draw its graph. So f, hit the enter key, there's the rule, and we'll use this tool called the plot builder. So plots. If I can hold my hand steady, we can go down here to plots, then select the plot builder. So the plot builder asks me what I want to draw, and I want to draw a 3D plot. So immediately I get this 3D plot. And it's drawn on a default minus 10 to 10 scale. Let's just lock that into place. And we need to modify this. I'm going to use some knowledge of what this surface looks like. Minus 2, I think. Maybe we'll try a 0 here too. And you'll notice that this goes up to 50, so maybe we can find a way to change the view. How about we view from 0 to about 10 and see what that does. Well, that puts us over here, so maybe 0 to 10 wasn't the right. How about let's try 8 to 15 maybe. So you can begin to see that you have a pocket down here somewhere. There is a minimum. Fool around some more, you get a better feel for where that minimum is. So graphical investigation. Surface. You could not do it with a pencil and paper. You have a tool here in Maple you can use to get a feel for where the extreme value might be. So now let's do a numerical computation. So there's the rule. And here in optimization, minimize, get a local minimization. So here is the local minimum. See the 9 something? And here's the x, and here's the y that locates that minimum. So preliminary messing around here, you get an idea of what this surface looks like and where extreme points might be. Now, there is a solution available via a task template. Now, what's a task template? Tools, tasks, browse. And this will bring up the table of contents of the task templates. So we have Multivariate Calculus. We are trying to optimize something. And you see there's this critical points and second derivative test. This is the task template that I want, and it can be inserted by these two buttons. Default content means you get this extra verbiage. Minimal content means you get enough to make it work. Now I've got that installed already here, and here's the path we just took to find this. So select the default function, type F and hit the enter key. The variables are x and y, so hit the enter key. And you notice that there are commands here from the Student Multivariate Calculus package. And the command here is gradient. Gradient has two components, derivative with respect to x, derivative with respect to y. You would set those equal to 0 and solve to find critical points. So the Maple solve command does not object if you don't put the equal 0. So it's going to take these expressions and use the data reached by these equation labels and solve for any points that might be critical points. There's extra coding here to put the solutions from solve into the form of a list of lists. Otherwise, you're going to have x equals, y equals, and that is not the right syntax for this second derivative test command. That's what's going to happen next. Maybe we'll look at any points in this list, that's equation label 7, and it will run a second derivative test on each of those points. There's only one point, so that point shows up here, and Maple says that point's a local minimum, and there are no local max or saddles. And then there is one other way of looking at this. Obtain the Hessian, which is the matrix of second derivatives. If that's positive definite, and you can check that because it's symmetric, all you need to do is look at its eigenvalues. If the eigenvalues are both positive, then it's a positive definite matrix, and then you're adding something locally around that critical point. So if you put your hands together in the shape of a bowl and run your hands up the side of that bowl, you're adding to the bottom of the bowl. That means the bottom of the bowl is a minimum. And these are clearly both positive. That one's positive. And the square root of 53 is less than the square root of 64, which is 8. So this is positive. And I include this here because typical calculus textbook does not give an algorithm for how to determine or apply a second derivative test to a function of 3 variables. And this is some insight into how you would do it for 3 variables. Well, to work from first principles, you would need to find the critical points, and you have to solve these two equations. So we could use the calculus palette, partial derivative with respect to x applied to function f. Now, whether or not you set this equal to 0 doesn't matter. Maple, when we go to solve command, Maple is forgiving with respect to that equals 0. We'll assume you meant to set it equal to 0. These are the equations you have to solve. You can use the simplest solve. And this is why there was that extra coding in the task template, because this, to use that second derivative test command, you would need to put this into the form of a list of lists. Applying the second derivative tests from first principles means computing this test number. So you need second partial with respect to x. So here is an operator in calculus palette, second partial with respect to x. Happens to be the number 6. You need a second partial with respect to y. That's 10. And then you need the mixed partial. So here's an operator for the mixed partial. I want y on the outside, x on the inside, so that it's dx dy. And that number is -7. The test number is the product of these two numbers, so that's 60, less the square of -7, so that's less 49. That's 11. This number is positive. This number is positive. What I would tell my students is positively positive. That positively positive case is this one. Critical point is a minimum. So probably after unconstrained optimization, constrained optimization might be tackled. And here's a problem in constrained optimization. We have an objective function, simple one, xy, constrained by this circle. Let's get set up here. I'm going to install the Student Multivariate Calculus package. Student Multivariate Calculus. Then the objective function, I've written this ahead of time to save a bit of typing time. F of xy, assign name. Then I wrote g equals, and you notice it's the function. Everything is brought to the left side, set equal to 0, but you just give the function. So again, assign name. This is clearly a Lagrange multiplier method problem. So it's possible to just get a solution which will be a Lagrange multiplier solution without any fancy tools. Use the context panel, make a sequence. There's the objective function. I could have typed just the name, the letter F. I'll just type G. So on this sequence, we go to Student Multivariate Calculus, and the only thing that Maple sees here that's applicable is Lagrange multipliers. What are the variables? The variables are x and y, and you could return a value. You could return a detailed value, or you could return a graph. I'm going to show you what happens if you return a value. You get 4 points. And then I think I'll go back and I'll do this again, and I'll show you what happens if you do a detailed value. So detailed value. So you get the same 4 critical points, but you also get the value of the Lagrange multiplier, and you get the value of the objective function. So there are 4 points. You have a 1, a -1, -1, 1. So there's too high, too low, and 4 points altogether. Now, there is a test template that will implement the Lagrange multiplier method. Here's the path to it. Function is f, the constraint function is g, variables are x and y, and this button executes the Lagrange multiplier method, and it puts the information in a nicer format. You read down the column. 1, 1 has the value, function value 1. Here's the -1, -1, 1, and the Lagrange multipliers. It's also possible to generate a solution from first principles. Here's one way to do it. I prefer this way rather than constructing gradient vectors. We write f minus, then we need a Lagrange multiplier. I'll use lambda, space for multiply, g. And I want to give this the name f. So I'm going to assign to a name, and that name will be f. So the 3 equations you need to solve are partial with respect to x equals 0, partial with respect to y equals 0, and the partial with respect to lambda picks off the constraint, so you have 3 equations and 3 unknowns. To take those partial derivatives, I'll use this calculus palette, partial with respect to x applied to f, and to show you that Maple doesn't mind that you don't say equals 0, I won't put equals 0. Y tab f, and once more, this time it's lambda tab f. These are the 3 equations we need to solve. I will tell Maple to solve these equations. Solve, and I think I'll pick the simplest solve, and you get the same 4 solutions, except you don't get the function values. And the thing that I would point out here is students find solving these nonlinear equations difficult because there's no rule, there's no algorithm. The only thing you can tell the student is don't divide by 0. And how do you prevent division by 0? Well, you don't cancel. What you do is you factor and use the 0 principle. If 2 things multiplied together equals 0, one or the other or both are 0. And that skill is hard to develop. So if you're trying to teach the Lagrange multiplier method, then it makes more sense to let Maple solve these equations until the student understands what the Lagrange multiplier method is all about. And then you can worry about the algebra of solving nonlinear equations. Then finally, there's one more thing I want to show you, one more tool. It's the optimization assistant, which is now in with the tutors. All right, optimization. This is now the optimization assistant. Okay, so I'll launch it from the context panel. And to do that, I need the objective function and the constraint equation, g equals 0. If I go to the context panel optimization, I have the optimization assistant, and the optimization assistant launches with the objective function and the constraint in place. Now, if I immediately jump down here to solve, suppose I'm looking for a maximum, and I say solve. Maple will say, I can't do anything because essentially I'm sitting on top of an extreme point. So if you want to see Maple do something, let's edit the default initial point. Let's go outside something bigger. Okay, so Maple finds 1, 1 with objective function value 1. But what I really want to show you here is that this thing draws a very nice graph. This is a graph of the objective function surface, but it's hemmed in, zoned in around the critical point. So let's back out a bit. Let's back out. Let's try minus 2 to 2. Minus 2 to 2. And let's redraw the graph. So now you see that you have a saddle surface. XY is a saddle surface. You have the constraint lifted to the surface. The constraint was a circle. And you have this point 1, 1 as a green dot. And if you graph the constraint as a surface, then you can see how that constraint got lifted to the objective function's surface, drawn in 3D. It intersects the surface. You get that nice curve in the surface. Let's take that away. Okay, so you can see where you're going to get these 4 critical points, too high and too low. So this is the tool that gives you this graph. And if you now click quit, you will get the result of that one operation there. You have found 1 point. You would have to repeat and search for the other extreme points.